In this chapter, we're going to learn about the atom. We're going to learn about what makes up an atom. We're going to talk about the properties of the atom. We're going to talk about how the individual components of an atom change as we look at different elements. So why is an atom of hydrogen different from an atom of oxygen or gold or lead or any of those things? We're also going to look at the structure or how these atoms have been organized, and we call that the periodic table. And you're going to have to learn a lot about the periodic table in terms of what different parts of the periodic table are called. We're going to have to learn about the names of the elements. Those things I'll list for you in this particular module. I'm not necessarily going to go over them all, but I'll give you a list of things to learn in this module. We're going to talk a little bit about the history. And there's not much you really have to know about the history, but there's some key players. I want you to know what they contributed. There's one experiment by Ernest Rutherford, and I want you to understand like how he interpreted data and how that influenced our understanding of the actual structure of an atom. And then at the end, we're going to understand how atoms, even though we think of all atoms of an element being the same, how those things are actually different from each other. There's variation, like flavors of ice cream, like Baskin Robbins has 31 flavors or something like that. And then at the end, we'll do some calculations, but these are relatively straightforward. I didn't say simple, but straightforward calculations that we'll go over at the very end of this chapter. So let's start with John Dalton. Okay, so this is one of those names that I want you to remember. And what he proposed was atomic theory. And I've mentioned his name before in the discussion of scientific method. Dalton really had three postulates and maybe a fourth, depending on how you count them. The fourth one is actually this one. This is like D, if you were going to count that as a fourth. But the first one is he just said, atoms are small. All matter is made up of atoms, and they're small and indivisible. And then he said, all atoms of an element are identical. So like if you had a hydrogen atom that you got from Reedley, and then you went out to San Francisco and got a hydrogen atom, he would say that those hydrogen atoms are all the same. And then he said that compounds are formed when you take two or more elements, different elements, and combine them to form a new substance. And that's how we get the idea of compounds. And then there was another postulate that he proposed, is that when there was a chemical reaction, atoms of an element would or atoms of a compound would reorganize and form new associations with other elements to form those new compounds. And we kind of know this now because we're perhaps more familiar with like formulas like H2O. We talked about that. And if you take H2O and you break it into its elements, you're going to get hydrogen and oxygen. All right, so this is a rearrangement of the atoms to form new substances, in this case the elements hydrogen and oxygen. So that was what John Dalton said, and there's a lot of history to that particular theory, which you could learn like in a Chem 1A class if you move on. But the next theory that I'd like to talk about is Rutherford's atomic theory. Okay, so just to give you a sort of a timeline of how all this worked, you don't need to know all the details on this timeline, but it was about 1800 that John Dalton proposed atomic theory, and then a guy named Joule, right, the Joule from the unit Joule, right, he discovered the idea of heat energy, so that's why his name gets associated with the unit. J.J. Thomson discovered the electron, or discovered the properties of the electron. He didn't really know what they were exactly at that point. And that was, again, in the early 1900s. So there's 100 years there. And then Rutherford in the 1919 sort of began to propose the idea of atomic theory. Okay, and then it wasn't until 1932 that we get the last of the subatomic particles, and we'll talk about those, the neutron. So if you think about that, that's less than 100 years ago that we sort of discovered one of the last components that is in every atom except for maybe one. Okay. So the next thing I'd like to talk about is Rutherford's gold foil experiment. And in Rutherford's gold foil experiment, let me explain to you a little bit about the experiment and then why it was set up. He took alpha particle emitter. Okay, so an alpha particle, I'm just draw it like this, and these are particles that at the time when you had a nuclear reaction, these were very large, okay, very massive particles with lots of energy that would fly out of the nuclear reactions, and they had been characterizing them. So you have these large particles flying out of an alpha emitter, okay, and it's in a lead box to protect people. He put a piece of gold foil here, a very thin piece of gold foil, almost atomically thin, and then he put a screen in the back. So what would happen is, if the gold foil wasn't there, when the alpha particle hit the screen, it had enough energy that it would create a little flash in the back, like that. Okay, and this screen wrapped all the way around like this, and it's supposed to be circle, but it's not. Okay, so the reason he set this experiment up was that his research professor, a guy named J.J. Thomson, the same guy who discovered the electron, believed that the structure of matter was a lot like plum pudding. See, they knew about positive and negative charges because of Thomson's work with the electron. He says, well, there's these negatively charged particles, there must be positively charged particles. So then the question was, how are these things distributed to create matter? So if you think about it, right, there's many different possibilities. You could have positive particles, which I'll do as blue, and negative particles that are like this. And they could just be evenly distributed in space, but he also knew that the positive charges were bigger because he knew that the negative charges were really small. So what he decided to call this, and I don't know why he decided to call this, but it was thought to be like plum pudding. So plum pudding is this smooth, like jello kind of, or pudding-like kind of thing, and it has plums in it. The plums were these big things, and they're just unevenly distributed in the pudding. And that was his first premise of how matter would be. Okay, so then the idea was, when you have these alpha particles and you pass them through the gold foil, they would hit a lot of these plums and be deflected by the plums because the plums were pretty big. Alpha particles also have a positive charge. Okay, that's actually a 2 positive charge. And so when they go through here and they see the plums, which have a positive charge, they'd be repelled by those, and then they would fly out in all kinds of directions. So, and the backstory also is that Thomson was tired of Rutherford and he said, go do this experiment and leave me alone. And I don't know if that's true, but I actually went to the university where he did the research, and some people said, yeah, that's the story we heard. So anyways, that's Manchester in England. They're really nice folk, I'll tell you. Anyways, so this is what he saw. All right, now think about this. You have a big particle, the alpha particle, and you have a wall of gold, right? Now think of it as you're in a car, right, like a semi-truck, let's say, a big truck, and you're going towards this gold wall, okay? What do you think's going to happen? All right, well, the thought is gold was actually, atoms were much more massive than the alpha particles, so the thought was it would just bounce off, right? So when they looked at the data, this is what 99% of the particles did. They went like this. And they made a little splash over here. Okay, so if you are walking towards a wall or driving towards a wall and you were about to hit it, and the next thing you knew you were on the other side of the wall, what would you think, right? And what you think is, well, maybe it wasn't there, right? Because you would automatically assume, like, if you'd have hit a wall like that, you would have felt it. And so here's the idea, okay? The first main observation is that the alpha particles, right, most went straight through. So what does that mean? Matter, this is the first major conclusion, matter is mostly empty space. So how empty, right? 99.9%, actually it's 99.99% of matter is open space. So let that sink in, right? Because you're looking at this on your computer. Roughly, right, 0.1% of that computer that you're looking at is actually solid. Okay, that's the first weird thing. The second weird thing is when they looked at the data, there were some deflections, and that's how they calculated the amount of empty space based on the deflection angles. But the other thing that happened, which was surprising to them, is that some of these alpha particles just were deflected straight back. So that's like you running, right, into a concrete wall and just bouncing off of it. And so the question was, what does that mean? And these actually the mostly empty space, and that some particles bounce straight back, go together. The conclusion is all the mass of matter must be condensed into really small spaces that make them really dense, okay? So matter, right, the mass is condensed into really dense regions. Because they had to be small, because not many of them got hit, so matter's mostly empty space. But matter has mass, so that mass has to go somewhere, right? And so when these particles would hit these really massive particles, the alpha particle would hit these really massive areas, they would bounce straight back, right? This is why we understand the nature of matter as being having a nucleus in it. So this is where we get the idea of the nuclear atom. The nucleus, that's what this is describing, of the atom, okay, is where all the mass of an atom is. So in the nucleus, there's actually 3 subatomic particles that are important for us in this class. The nucleus contains the protons and electrons. Or sorry, neutrons, protons and neutrons. Okay. Protons and neutrons make up most of the mass of an atom. And then there's the electrons, okay? So the electrons are very small, right? And they're about 1/1800th of the mass of a proton or neutron. Turns out the protons and neutrons have the same mass. Okay, so let's talk a little bit about their properties. But let me just go back over what I just said, because it's kind of important to understand. In the nucleus, you have protons and neutrons. That's where all the mass is, right, in the middle. And then the electrons are in all the space around the nucleus, okay? Now, protons have a positive charge, and electrons have a negative charge. And neutrons, because of their name, maybe you guessed, these are neutral. So these have no charge. Okay. So, the mass, right? Protons and neutrons, we could give their mass in kilograms, but it's this really small number, like 10 to the minus 31, and it's really hard to sort of keep track of it. So there's a unit that we call the atomic mass unit, and we'll go into that later in this chapter. But to make life easier, we essentially decided to call the mass, okay, of 6 protons and 6 neutrons, we said that would be 12. Okay, this is the actually comes from carbon. So this means a proton has a mass of about 1 and a neutron has a mass of about 1. And we call this mass unit, this relative mass unit, an atomic mass unit. So a proton has a mass of about 1 atomic mass unit, AMU, okay? And an electron has about 1/1800th of that, so we basically think of the electron having almost no mass. Now, there's a thing called Coulombs law, and we'll come back to this idea in just a second. There's an idea that we call Coulombs law, and in Coulombs law, it's basically that oppositely charged particles attract each other, and similarly charged particles repel each other. So when you think about the way the atom looks like, and sort of in our head, right? We have a nucleus that's here, and the nucleus has a positive charge because it has the protons, right? And then there's neutrons in there. And so the electrons are on the outside. They fill up all that extra space around the nucleus that creates like the matter that we see. So electrons are on the outside, and they have a negative charge. Okay, so here's an important concept. All matter is electrically neutral. That is, when you measure the charge of matter, it has as many positive charges as it does negative charges. And so one of the things we know from Coulomb's law and the idea of charges is that all matter being electrically neutral, in an atom, the number of protons equals the number of electrons. Okay. So then Coulomb's law, though, also says something else. Think about 2 atoms, right? And there's a positive charge here and a negative charge here. And remember, the electrons are these small things that fill up this space around the nucleus. And you take another one with a positive charge like this, right? And what Coulomb's law says is this negative charge is going to be attracted to that positive charge, and this negative charge is going to be attracted to that positive charge. And they find a happy in between where they can be attracted to each other and stuck to each other. And this is really the reason why, like when you because remember I said matter is mostly empty space. You just can't take your hand and shove it in between the matter, because those atoms, right, their electrons and protons create what we call chemical bonds. So this idea of positive, negative leads us to the idea of there being chemical bonds between elements. And that's why you can't just like walk through a wall or stick your hand through something, okay? All right, so the next thing we'll be covering is the components of the periodic table.